Like I said before, most of this course is a KAQ equation. Okay, we just call them different things in different units. All right, so excuse me. So when you're writing, if we have aluminum chloride, we throw it in water. It's an ionic solution, so it ionizes to aluminum and 3 chloride ions. What's the KAQ expression for this? Concentration of aluminum times concentration of chlorine to the third power, right? And we don't include the aluminum chloride because aluminum chloride is a solid, right? Solids and liquids are not in there, okay? All right. Really what this is the dissolving of aluminum chloride. Okay, so that's why we give it a special name. Instead of calling it KEQ, we call it KSP, the solubility product, or the solubility constant. Okay, because really it's relating how much of it will dissolve in water, because this doesn't show up in the KEQ expression. Okay, so KSP expression for sodium bromide. Why does my pen not work? Breaks up into sodium and bromine. We should write AQ. So the KSP is just the concentration of sodium times the concentration of bromine. Pretty straightforward. If you're going to do it for ammonium sulfate, what would that be? Remember, just like Maya pointed out, we have to balance everything. Okay. So it's just basically relating how much of it dissolves. So the higher the KSP value, what can you say about that salt? The more soluble it'll be. All right. So it relates directly to solubility. And they can be really big numbers or they can be small numbers. So really, really small numbers. So if you have sodium chloride, we get a saturated solution when 3.5 moles is dissolved in a liter of water. If you write out the balanced equation, NaCl goes to Na ion, sodium ions, and chloride ions. They are equal. So the concentration, if we have 3.5 moles of this, then you have 3.5 moles of this and 3.5 moles of that. It's a 1 liter container, so that's the molarity. Does that make sense? So if I want the KSP, so these are both 3.5 molar, the KSP is just (3.5) times 3.5, which is 12.25. And if we're going to go with sig figs, we'll write it in scientific notation. 1.2 times 10 to the 1, or just 12. Okay, again, KSP, just like KEQ, has no units. Yep. Sorry? Oh. Yeah, because it's essentially a KEQ. All right, so it has no units. But silver chloride has a low solubility. Okay, so it becomes saturated when there's 1.34 times 10 to the minus 5 moles. Okay, are dissolved in a liter of solution. Silver chloride, again, is a 1-to-1. So silver chloride goes to that. So if I have 1.34 times 10 to the minus 5 moles of those, I have the same amount of silver and chlorine ions. So I have 1.35 times 10 to the minus 5. Actually, it's 4. And same for chlorine. So the KSP is 1.34 times 10 to the minus 5 squared. Which is 1.80 times 10 to the minus 10. So a really small KSP. Okay. Does that make sense? So KSP will tell you how soluble something is. If it's highly soluble or has low solubility. Now, solubility and KSP are different. Okay? And students mess this up quite a bit. So, the value of the KSP is related to the solubility, but they're not the same thing. Okay? So if I said, what is solubility? Can anybody give me a definition or what you think would be a definition? If I just said, what's the solubility of salt, sodium chloride? It's the amount in grams or moles that you can dissolve in a certain volume to get a saturated solution. That's the definition of solubility. All right. So solubility will be the amount, whether it's grams or moles, or produce a saturated solution. To reach or produce a saturated solution. Whereas the KSP, the solubility product, this is KSP, is, I'll just say the number produced when concentrations of products are multiplied together. So they are related, but they are not the same thing. If I say the solubility of something, I want to know how many grams or moles you can dissolve per liter to get a saturated solution. If I say what's the KSP, you're using the solubility and the concentrations to generate that number using a KEQ equation. All right. All right. We'll just do one more example and then we'll be done. If you look in your data package, we're going to start using our data booklet quite a bit now. If you scroll past the solubility chart that you were just using, you get to the KSP chart. Okay, we will use this a lot. All right, so it gives you the solubility, the KSP, the solubility products of various compounds at 25 degrees. Why do we have to specify temperature? Because KQ, just the same as KSP, will change with temperature. Okay, and you can see some things like iron hydroxide has a very low KSP, 2.6 times 10 to the minus 39. All right. So this is going to be a reference page for you going forward. Okay. Excuse me. We'll do one calculation here, and then that'll be it for today. So, all right. They tell us the solubility of barium fluoride is 3.5 times 10 to the minus 3 moles per liter at 25 degrees. What is the KSP? Okay. First thing, write out the ionic equation. The dissociation equation, I guess I should say. So BAF2 becomes barium plus 2 fluorines And that's a solid. Solid. Those are aqueous. Aqueous. Remember, always balance it. They've given us the solubility in moles per liter. So if we have 3.58 times 10 to the minus 3, I know it doesn't make sense to have that in terms of molarity, but we'll just pretend it does. What's the concentration of barium ions? It's going to be the same, right? Because it's a 1-to-1. There's one barium in one molecule of this. What's the concentration of fluorine? It's double that. It's 2 times that. So then if they're asking for the KSP, it's the concentration of fluorine squared times the concentration of barium. What is this? I don't even know. 7.16 times. So if you punch that in your calculator, you should get, hopefully, 1.84 times 10 to the minus 7. Does that make sense? All right. So that's the, I think that was even, or no, the next question is the bonus question that was on the test. So basically, if I give you the solubility, which will always be in moles per liter or grams per liter or some sort of amount per volume, you write out the dissociation equation. Remember to balance it because these coefficients will increase or decrease the concentration depending on the ratio. Then you write the KSP expression, and remember that the coefficients become the exponents in the KSP expression. All right, so it's just like the KEQ stuff that we did last chapter. I would just like you to do question number 1, and then we'll pick this up on Thursday, I guess, because tomorrow we're doing the lab. Yeah, I guess. I don't know. I don't know what I'm doing. I can't answer that question.